basically you guys already familiar with what's the scanning probe microscope, right? So scanning tunneling microscope and atomic force microscope are already given to you. Okay, particularly the first class, right? So particularly STM, scanning tunneling microscope, allows to see directly see what's going to happen at the molecular or nanoscale. Okay, so many guys say that the conceptualization of nanotechnology has been initiated by here Richard Feynman, but this realization is boosted by the invention of the STM, right? STM, as you already know, that's depending on the scanning tunneling effect between the two metallic nanostructure, both of which are close with each other with molecular or nanoscale distance, right? So in principle, scanning tunneling effect is quite sensitive to the distance between two metallic objects. Okay, it's quite sensitive even to the molecular or atomic scale. For example, Armstrong scale, something like that, right? So that's main reason why the STM allows to directly see what's going to happen at the molecular and nanoscale. The problem is like that the STM technology, STM scan tunneling microscope cannot be well democratized for a newcomer or expert alike because they need to be vacuumed at the relatively highest level, right? Okay, so such vacuuming required huge and specialized facility with relatively big volume. That's not so common to newcomer or expert alike. Okay. Also, the substrate for STM should be limited to the metallic. Okay, metallic substrate because that's depending on the scanning tunneling effect, right? So later on, the guys working in SPM trying to generalize this scanning probe microscope, and that effort lead to the invention of AFM, atomic force microscope. So as we dealt with it before, the AFM rely on the atomic force, fundamental atomic force, for example, Van der Waals force, rather than scanning tunneling effect. Okay, and as I emphasized before, Van der Waals force can be considered as the universal fundamental force because they are everywhere, right? Van der Waals force can be observed in everywhere, regardless of material species, material element, size, structure, and Van der Waals force exists everywhere, right? That's the reason why people are saying that Van der Waals force is universal, and among the other fundamental force, Van der Waals force is the most important. Okay. Such generality make AFM more compatible with the common technology in terms of seeing something. But what I want to emphasize today is that the AFM is not so restricted on the visualization of something at molecular nanoscale. That also allows to make something in highly efficient way. Okay. So that's the main motivation why the SPL, scanning probe microscope based lithography, becoming quite important over the last 3 decades. The first concept has been reported, was reported a pretty long time ago. That's about almost 30 years, 30 years ago. That also firstly pioneered by IBM Research Center. So as you already might recognize, many of research innovation, particularly related to the nanoscale fabrication, has been led by the IBM actually. And later on, the SPL related technology has experienced a lot of technological advance in terms of the high throughput, and resolution, etc. So today we're gonna briefly see what's going to happen in terms of SPL technological advancement. And this SPL is more also related to making something at nanoscale or even molecular scale. So this technology could be more related to how the computer becoming smaller and smaller, or how we can store more information in the given volume. Also, that's also pretty related to directly see something at molecular nanoscale. Okay, so this image already given to you guys in the last structure, and yes, so let's imagine what's going to happen if we can make some pattern uh, through lighting. Okay, our common line we are generally doing like this, right? So by using your pen, you can put some arbitrary letter onto the substrate. Here, substrate is the paper. Okay. So some daunting feature of this kind of nanofabrication, lighting or letter, could rely on that nearly arbitrary pattern, whatever you want to have, can be written onto the substrate, right? So the possible problem could be like this. Okay, so this some sort of the serial method, right? So okay, so by writing something, we can put the arbitrary pattern, but each writing resulting in relatively small unit of structure. Okay, for what I mean by here is that by using writing letter by your pen, each individual unit or structure can be written in serial way. Okay. But how about the photolithography, or how about the photolithography? Some many of structure what you want to have can be parallelly developed, right? Some such array can be defined by the photo mask, right? So you can put the blueprint onto the photo mask, and given the area of the photo mask, you can put a lot of structure simultaneously, and such a blueprint containing a lot of structure can be parallelly translated into the photoregist. So people say that this is some sort of the parallel method or parallel philosophy in terms of making something. But making the structure through this kind of writing with your pen is in stark contrast what the photolithography can do, right? Just one structure can be written or developed by your writing with your pen, right? So intrinsically, the throughput of this kind of method could be much lower than that of the photolithography and so on. Okay, that could be possible problem. But anyhow, it's quite appealing because the nearly arbitrary structure, shape, or geometry can be assessed, right? So many people, this philosophy drive the motivation of SPL, scanning probe lithography. Okay, so this image already given to you guys, right? So we can start with the pen, quite sharp pen, with molecular scale sharpness. Okay, so generally this pen can be taken from the AFM, and by using this kind of nanoscale or molecular scale pen, we can write the structure, nearly arbitrarily structured something can be written in serial way. Okay, So common thread is like this. The use of Sharpie scanning probe. That's actually tip. And we can induce the modification on a surface. Okay. Such modification can be induced by several way actually. So it could be mechanical way, also it could be chemical way. Okay, for example, we can put the heat in the local region. Okay, so through putting such a heat in locally, we can induce some surface modification. Okay, for example, some surface relief can be newly generated, or also we can induce the local evaporation of resist selectively where the heat is applied. Okay. Also, the because we are depending on the nanoscale or molecularly sharpie tip, such a local modification can be induced with also resolution which could be comparable to the sharpness of the tip what we use. Okay. So SPL generally used to image, but also can be used to modify or manipulate the surface at nanometer or atomic scale. Okay. And then let me introduce what's the key factor of SPL. So key factor can be categorized into two main things. So first, we should use the Sharpie tip in contact or near contact with the nanoscale region of a sample surface. Okay, and then by putting external stimuli through this Sharpie pen, we can induce the surface modification. And such external stimuli could be mechanical, thermal, electrostatic, and chemical interaction. Okay. Also, in case two or three kind of external stimuli listed in here could be combined to make a synergistic effect between them. Okay. Okay. So that's the first main feature of SPL. Also, as you already know, the SPM technology can be mainly categorized into two things: scanning tunneling microscope and AFM. And most of the SPL depending on the AFM rather than STM, because AFM is more easy to operate and is more easy to access, especially at the university level. So the development history of SPL mainly done with the AFM rather than STM. Okay, so that's another key feature. So the historical advancement of the SPL technology, what we gonna deal with it, is mainly related to AFM based technology. Okay. Yes, so it's time to introduce what kind of the external stimuli has been used to do SPL. So, specific literature here, published in Nature Nanotechnology 2014. They introduced the criteria how we can categorize the SPL technology reported thus far. So basically, they categorized with respect to how we can pattern. For example, let's say we're gonna have the register, and by using scanning probe, we can selectively remove the material. Okay, And also we can selectively add the material. So according to this kind of the material patterning philosophy, this SPL reported thus far can be categorized into two. Okay. And also they added the argument like this. The material removal is based on with the physical stimuli. Okay, for example, we can put some heat to induce the evaporation of the resist. Okay. Also, we can add the material. Okay. So that's mainly done by. They can be mainly done by some chemical approach. Okay. So the most famous technology about this chemical-based SPL could be deep pan lithography, what the Chad Mackin and Northwestern pioneered about 2 decades ago. Actually, so let's say we're gonna have the tip, okay, like this, and the at the this tip could be inked with specific chemical, okay. So much like the writer letter with the macroscopic pen, okay. Some this nanoscale tip inked with specific chemical also can be used to write a letter at the nanoscale or even molecular scale. So as we will discuss in greater detail, this the used chemical toward this deep pan lithography was mostly self-assembled monolayer. We already discussed it, right? So let's say we're gonna have the alkene chain, uh, where the one end is terminated with silyl group, can be used as ink to write a letter onto the surface of gold because this silyl group anchored at the end of alkene chain can allow them to dock onto the surface of gold, right? So through that, you can write the letter fully made of the self-assembled monolayer. Okay. Also, as we discussed already before in the part of the software lithography, self-assembled monolayer can achieve almost 100% Arial factor, right? So which in turn allows to use it as a mask for etching out the below gold, right? Okay, so Dante feature is like that. This accessible resolution with this kind of depend lithography can be reduced or below the few micro or can be comparable to the nanoscale. Okay, so before the invention of this kind of SPL technology, such ultra high resolution could be achieved almost only with e-beam lithography, right? But e-beam lithography also suffer from the problem what photolithography or STM have, right? So the use of e-beam lithography facility is not so easy, particularly at the university level. Okay. So such problem was more elucidated at the time of about the 1990, something like that. At that time, the fabrication of micro and nanostructure was not so democratized, right? That's the main reason why many people conceived the concept of unconventional lithography, as we discussed before. Okay, anyhow, so what I want to emphasize in this slide is that SPL could be also categorized like this, okay, according to the material removal or addition, or according to the physical or chemical approach for induced patterning effect, okay. So due to the time limit, we cannot cover all of them. Just let me introduce the representative technology in each part. Okay. So first could be physical SPL, and that was started very long time ago, about almost 30 years ago. So this paper is the first report on the summer SPL. So here, physical SPL depended on the summer energy as external stimuli. So they can concentrate the heat energy onto the Sharpie tip, right? So we can induce the summer energy, induce the modification of the substrate. Okay, so particularly what they found out that PMMA here, polymethyl metacrate, this had been widely used as a photoresist, okay, particularly for e-beam lithography, right? And what they found out that they can put the Sharpie AFM tip at the AFM tip. You can concentrate a lot of heat energy, particularly far beyond the glass transient temperature of PMMA. Okay, so you already learned about what's the glass transition temperature, right? It's pretty different from the melting temperature. Anyhow, so the heated tip, we can bring it to the surface of PMMA layer, and then we can locally induce the melting effect of PMMA, right? So it's going to be melted selectively where the heat is the induced. So we can induce the locally fluidized movement of PMMA, right? So through that, we can thermally induce the surface modification fully made of the PMMA. Okay, and we can repeat this process until the desired pattern is fully developed, right? So through that, we can do some patterning like this. Okay, so heated tip can be put onto the surface of the PMMA here, here. So through repeating this kind of process, so many dot can be written onto the surface of PMMA, and we can repeat until the desired pattern is fully developed. Okay. So here, according to the dwell time indicate that how much time tip can be reside with the contacting to substrate. Okay, we can say that it could be dwell time. So according to the dwell time, the accessible feature of this relief could be precisely controlled. Okay, so according to when the dwell time is reduced, the feature size can get smaller and smaller. Quite simple and quite effective method. Okay, so this slide also show the schematic for the facility what they used. As I mentioned before, basically they used AFM. Okay, so here is the cantilever or tip. So tip is also called cantilever. And this actuator is based on piezoelectric effect. So this actuator allows to control over the distance between tip and PMMA substrate. And particularly also you need to focus on what's that thing. So they shoot the tip with the laser, and at the top of the tip here, cantilever tip could be relatively flat. So incoming laser with specific instant angle going to be reflected with the same instant angle like that. Okay, so here we can put the detector to monitor in situ to monitor the intensity of the reflected light. So the reason why they use this kind of laser illumination and reflection system is like that. So let's say here is the substrate and here is the tip, and you need to figure out the distance between tip and substrate in situ way, right? Situations. And the distance between tip and substrate is quite small, like the few nanometer or even much smaller than few nanometer, something like that, right? So it's quite difficult to directly visualize the distance between tip and substrate, right? So they take a bypass to monitor the distance between tip and substrate. For that, they use this laser illumination reflection system. Okay, so according to the tip distance, tip here generally AFM tip is designed to vibrate. Okay, it's going to vibrate, and according to this vibrational position in terms of vertical direction, they should feel difference Van der Waals force, right? So as we discussed before, basically Van der Waals force is quite sensitive to the distance between two objects, right? So when the tip get more close to the substrate, they should feel more stronger Van der Waals force. Anyhow, according to the degree of Van der Waals, what the tip could feel, the vibrational frequency going to be changed, right? and and the change in frequency vibration frequency or the change in the vibration of cantilever tip, this reflect the intensity of light reflected from the top surface of cantilever tip could be also changed. Okay, so let me repeat again. We should figure out the distance between tip and substrate in situ way, right? And we cannot directly see such a distance between tip and substrate because basically the optical microscope to prove the tip position is done with the vision machine placed at the top, so we cannot see the cross-sectional view in situ way, right? So also the distance between tip and substrate is generally quite small, right? About a few nanometer or even smaller than, okay? So in common optical microscope cannot access to such a small distance. So that's the reason why the researcher working in the AFM take over the bypass. Okay, that's the related to using the laser illumination and reflection system as indicated here. So AFM basically designed to vibrate. Okay, they designed to vibrate, and according to the distance between tip and substrate, the degree of Van der Waals force, what the tip could feel, also could be changed, right? Okay, so the frequency of cantilever tip vibration could be also changed according to the Van der Waals force between tip and substrate, right? And the resultant to the Van der Waals force. So such change in frequency of the cantilever tip vibration can be monitored in highly precise way via the in situ monitoring of the intensity of reflected light. Okay. According to the vibration, the intensity of reflected light also can be changed. Okay, through that, we can monitor the distance between tip and substrate in situ way. Okay. Also, we can basically keep the optical microscope. Here, while light laser is going to be used as the source for optical microscope vision system. Okay, so light going to be focused at the top. So in order to figure out the position of the AFM cantilever tip. Okay, so through this optical microscope, we can figure out where our cantilever tip is placed. Okay, so after recording one structural feature, we need to move on to the neighboring position to define the another structural feature. Okay, so that's the first report on the uh, physical SPM, particularly based on the thermal energy as an external stimuli. Okay, so later on, this thermal based thermal SPL is further advanced to making the structural feature with 3 dimension as well as 2 dimension. Basically, the initial version of thermal SPL was limited to 2 dimensional patterning, but this 2 dimensional patterning has been further expanded to the 3 dimensional counterpart. With that work was firstly pioneered by this paper. Okay, so basically, this slide indicate the tip what they used. Basically, the architecture of cantilever tip what they use is basically same with what we have discussed in previous slide. Okay, so if you look in more great detail, we can see the tip is in here. Okay. Also, this tip is connected to the capacitive platform. Capacitive platform is that they can precisely control over the temperature, which going to be put at the tip of at the end of this tip. Also, the other side of the tip is connected to the other cantilever. They're going to use to figure out the distance between the tip and substrate. Okay. So first, they should figure out the position and distance between tip and resist, and then once they figure out the desired position where they want to put some structure, the tip can be designed to get more close to the substrate, here resist, and then he could be applied. Okay, so through that we can record each individual feature. Okay, so this slide provide you about the information of resist what they use at the time. At the time, they used quite specialized chemistry for thermal-based SPL. Here is the molecular architecture, what they architecture of resist what they used. So basically, it's composed of the aromatic ring, as indicated here. Here's enter the aromatic ring going to be branched out with 3 arms. And each arm also further branched with two arms. So daunting and the most critical feature of this molecule is that they have the 6N, 1, 2, 3, 4, 5, 6, and all ends of this molecule is terminated with hydroxyl group, like this. This implies that this each individual molecule going to feel strong hydrogen bonding between each molecule. Okay, so they should strong, much like the water, right? So at the room temperature, it can exist as a full solid phase, but once we put the enough thermal energy far beyond enough thermal energy to break this hydrogen bond, the largest molecule he indicated here can be vaporized. Okay, so as we discussed before, heat which is enough to induce vaporization of the resist we have seen we what we saw just now. Some such resist can be selectively and locally vaporized. Okay, so through that you can light the or record the individual pattern like this. So here is the representative example toward this end, right? So what you can see here is that somewhere this heat is applied is selectively evaporated, vaporized some, and the other region is remained almost intact. Even if we can see some bumpy surface, but basically the area where the heat or thermal energy did not thermal energy was not applied is remained almost intact. Only the area where thermal energy is applied is vaporized. Okay. So particularly they achieved pretty high resolution, feature resolution about tens of nanometer. Particularly they achieved feature size can be reduced to 33 nanometer. Okay, so also you guys, everybody in here want to publish the science and nature paper, right? So toward this end, you guys need to have the show up data. So they show that the method also can be compatible with the three-dimensional patterning as well as the two-dimensional counterpart. Okay, so basically the writing a letter with pen should be compatible with the two-dimensional surface rather than three-dimensional surface, right? But in this case, it's much like the carving something, right? Carving something. 조각. 조각하는 거와 비슷하죠. So they found out that their method could be highly compatible with the 3D patterning. Okay, so we can start with the volumetric resist like this, and this volumetric resist going to be carved. Okay, to make the three-dimensional shape. Okay, so particularly they make some structure which appearance is quite similar to the specific mountain, right? I cannot exactly remember what's the name of that mountain. So let me quickly check it out. What's the thing? Uh, yeah, so there's a Matterhorn. in Swiss. Yes, this is the actual real image what the Matterhorn is looks like. Okay, so nanoscale Matterhorn was developed by Summer SPM. Okay, it's quite good to have the three-dimensional nanoscale something, right? Also, nearly arbitrarily shaped either three-dimensional structural feature also can be assessed. That's another key advantage of this technology. Okay. So they depended on the specific chemistry of the resist. So we can also say that this technology is thermochemical method as well. That's just not purely thermal technology. Previously, we see that by putting the thermal energy, we can induce the flow of the polymeric. Okay, that effect can be induced highly local region. Okay, locally induced the flow of the polymer by using heated AFM tip, right? So that's more related to pure physical effect, right? Just put the heat to the polymeric resist, and we can induce the local flow of polymer, right? So we can say that that can be included in the category of pure physical effect. But in this case, they depending on the specific chemistry, okay, to selectively and locally vaporize the resist where the heat is applied. Okay, so that's reason why we can say that it's more like the thermochemical SPL. Also, we can use the different chemistry to selectively induce the vaporization of the resist. Okay, here is the specific polymer with the name of PPA, and also we can put the high temperature about the 700 Celsius degree with relatively short time, we can induce the chain scissoring effect in this polymeric chain. Okay, this polymer can be transformed into this kind of monomer by using the relatively high temperature treatment throughout the AFMT. So this at that time they call this effect is depolymerization. Also, it can be called with the term chain scissoring. So it doesn't matter whatever terminology we're gonna use. Anyhow, through this kind of specific chemistry, we can locally induce the evaporation of the resistor. Okay. Only region where the heat is applied. Okay. Also, that method, they also make quite sophisticated pattern. So basically, it's composed of a Spinsky triangle. This is quite good in terms of making the arbitrary pattern, even if throughput should be relatively low particularly compared with the porosity, because each individual feature should be developed individually. So people, let me repeat again, this kind of philosophy is generally denoted as serial method, okay? And porosity is the parallel method. But the arbitrary pattern can be assessed with this method, much like the e-beam lithography. But the required facility in doing such kind of serial patterning is could be much more democratized in the case of the SPL. But for the case of e-beam lithography, we need to have electron microscope first. For example, scanning for electron microscope SEM. We also have to have vacuuming that with a relatively high level. It's also not so easy to assess. Okay, but in this case, we can depend on the common AFM, which are commonly found in the university. Also, our graduate school have it in the KU R&D Center fourth floor. Okay, so this kind of summer chemical SPL technology contributed to generalization of the micro nano technology as well. And also some guy thought that using the heat with relatively high temperature, for example here 700 Celsius degree is also not so good in terms of generalization of this technology. So some guy working in the nanoscale assembly of a polymer conceived a new idea, doing similar thing without heat treatment. Okay, so particular Professor Jin-Gon Kim at Postech Chemical Engineering Department, and what he found out that some polymer, specific polymer, is called by Bracco polymer, can be deformed just by mechanical pushing with AFM tip. So particularly some specific Bracco polymer composed of polystyrene or polypentyl methacrylate block can form this lamella assembly. So generally the Bracco polymer indicate that two different polymeric block is covalently linked. Okay, so these two block is designed to repel with each other. Basically, this the block in the block of polymer is designed to have quite different chemical affinity. So basically, they tend to repel with each other, but they still strongly engaged with each other because these two blocks with quite different chemical affinity are covalently linked with each other. Right, so they tend to repel, but they still need to be strongly engaged through the covalent bond. So this kind of a competition, they can be assembled into this kind of beautiful nanostructure with quite a variety of morphology. So here morphology is generally defined by the molecular weight or molecular weight ratio between two blocks. Also the degree of difference of the chemical affinity between two blocks can affect the assembled morphology as well. Anyhow, the important thing in here is like this. They found out that this block polymer can be assembled into this kind of lamella structure. And this block polymer assembly can be deformed when they are pushed with this AFMT. Okay, so when the AFM is push the surface of this block polymer assembly, they're going to be changed. Their surface morphology going to be changed like this. Okay, somewhere the tip is tip pushed can be deformed like that through the local disordering of the block polymer assembly. Okay, so through this method, they found out that surface relief can be developed by pushing with AFM tip without any kind of thermal treatment. So morphological change can be induced even at room temperature. Okay. So through that, they recorded whole array, regularly arrayed over the large area, and each hole have the tens of nanometer in diameter. Okay, so this resolution was found to be comparable with what e-beam lithography can achieve, right? So just with the AFM, without any heat treatment, without any vacuuming process, such nanoscale feature with tens of nanometer in diameter can be recorded over the large area. Okay, so this can further promote rapid uptake of the SPL technology for making nanoscale structure over the large area. Okay. So I think that's all about the physical SPL. Okay, so let me repeat again. Due to the time limit, we cannot cover all about the physical SPL developed so far. Just now I gave you some representative example to the physical SPL. Okay, so let me wrap up the first part of the SPL here.